Hi everyone, my name is Pradyum Shum, and I'm a rising senior majoring in computer science at the University of Illinois at Urbana-Champaign. Today, I'll be talking about PRISM, protections impeding side channels in microarchitecture. This work is done in collaboration with Jose Rodrigo Sanchez Vicarte, affiliated with the University of Illinois at Urbana-Champaign, Adam Morrison, affiliated with Tel Aviv University, David Kohlbrunner, affiliated with UC Berkeley and University of Washington, and my advisor, Chris Fletcher. So what is a side channel attack? Well, a side channel attack is one which extracts private information from a program based on the implementation of an algorithm and not an algorithm itself. If you look at the code snippet on the right, check is a subroutine that accepts a secret input, iterates to every bit B in it, and if a bit B is set, it sleeps for some amount of time. Now, an adversary that is able to measure the execution time of check at a fine granularity can learn the number of bits in secret that are set. And from there, figure out what secret is. And all of this is done without explicitly transmitting information about secret. Side channel attacks in the literature can be divided into two periods of time. Pre-spectre, that is conventional side channel attacks that rely on side channels such as the state of a processor's shared cache, or LLC, or the timing of functional units such as, say, floating point units, to learn operands of instructions based on their behavior and other microarchitectural structures. The second category is Spectre and beyond. So in 2018, two attacks rocked the security and architecture communities, known as Spectre and Meltdown, which exploited the side effects of speculative execution and out-of-order execution to learn all of program memory. Now, what is speculative execution? It is an optimization found in today's modern microprocessors, which enables a processor to do work before it is known to be necessary. One popular example of this is in branch prediction, where a predictor can predict what direction a branch is going to go and what is the branch target. Now, by running instructions down one particular branch before it is resolved, you can actually save a bunch of time, because if the prediction ends up being correct, you can continue execution at the point you left it. However, if you mispredict, what happens is you need to undo all the instructions that were transient or those whose validity was not determined yet. And you need to resume execution from the point of misspeculation. Unfortunately, however, not everything can be undone. In fact, changes to the cache due to memory accesses and stores remain. And this particular fact is exploited by these attacks to leak sensitive information. So let's quickly do a deep dive of Spectre variant 1. In this attack, an attacker wants to learn the secret value V stored at address X in a program's memory. We assume that the cache line size is 64 bytes and that V is a 1 byte variable. So this attack can be divided into two pieces of code that the victim runs and code that is run by the adversary. So on the victim, there's an array A that is of size 10, and B, which stores 256 possible cache lines. And since our secret value has space 1 byte, there are naturally then 255 possible or 256 possible values of V. So victim is a function that accepts an index A, and if the bounce check is successful, we perform a memory load into B. Now, what the attacker can do is run a subroutine called train, which can bias the branch predictor into predicting this if condition to be true. And this can be run on, say, another core of the same processor. And the next step is if the attacker flushes B, um, what this means is that subsequent memory accesses to B will be served from main memory, which is slower. In the next step, the victim function is called from the adversary with argument x minus the address of A, which is our array here. And what happens here is, since we biased our branch predictor, A, even if it is out of bounds, will be predicted to be in bounds. And essentially, we'll be able to run this memory load on some arbitrary address A. And this is essentially the secret sauce, that we can actually pick whatever A you want and have it be loaded into a processor's cache. And yes, you're right that after a while, the processor will realize that this condition is actually false and will actually perform what's known as a squash. However, that's too late because the secret value is now in the processor's cache. So now if the adversary scans B, and that is by scan, I mean access every cache line, they can actually time the accesses and figure out, based on which access took the least amount of time, what the value of V is, since the Vth cache line in B is loaded into the cache, despite the fact that the load is eventually squashed. And this is how an attacker can essentially leak all of program memory without really performing some kind of privilege escalation or other attack. So if speculative execution is so dangerous, why don't we just turn it off? It turns out that it's not so simple. From Intel sources, you can learn that speculative execution, if completely turned off, results in a performance penalty of almost 9x, which is unacceptable by most people today. And a good question to think about from today's presentation is, why is it such a drastic performance benefit? And what is really happening? Like, how are we getting this huge benefit by speculating? So since we can't turn it off entirely, we need to come up with various ways to prevent such attacks and similar attacks from happening in the future. So there have been a number of software patches that have been suggested. However, the issue with software patches is that they're very point fixes, which can be circumvented with not a lot of effort. So researchers in the hardware security community have come up with a variety of hardware-based mechanisms to prevent such attacks, 3 of which that I'll be presenting today. So the first one is called invisible speculation, or invisispec. It is a technique that prevents transient loads, that is loads whose validity hasn't been determined, from affecting the cache hierarchy until they're determined to be safe. So by using something called a speculation buffer, we perform these loads in a safe manner and only allow their effects to propagate to the rest of the architecture once we know that it is safe to do so. The second method is known as DOG, or dynamically allocated wayguard. Today's caches are usually set associative, meaning there are multiple ways for each cache line, which reduce conflicts. So by partitioning the cache and by allowing certain cores to only access certain ways, we can actually create and show these non-interference properties that prevent an adversary from learning about the cache behavior of victims and vice versa, which prevents the attacker from leaking information about any secret data that the victim may have accessed. The third method is called speculative taint tracking, which is an intelligent way to turn off speculation. So by using this method from programming languages known as dynamic information flow tracking, you can actually track whether an instruction is safe to speculate or not, based on if it is in any way related to a secret input. So by tracking how variables are essentially created, and if they're related to anything marked as secret, we can actually turn off speculation until it is safe to do so. And these are the 3 methods. I am very excited that some of our work on side channels We're going to submit this to ASPLUS 2021. And I wanted to take this opportunity to thank my advisor, Chris, and my mentor, Jose, for taking the time to mentor me and guide me and make me a better researcher over the past year or so. And if you are interested by any of the work presented today, I encourage you to read the original papers. The first few are a bunch of side channel attacks, and the rest are the protection mechanisms I talked about today. Thank you so much for listening to my presentation.